8 days. That's all we have left. 8 days. Before an interstellar comet, traveling at 68 kilometers per second, disappears behind the sun, hidden from every telescope on Earth, invisible, untouchable, alone with our star. Its name? 3I Atlas. The third confirmed visitor from beyond our solar system. Not born here, not from our neighborhood. A wanderer from the deep cold of interstellar space. And here's what makes your spine tingle. This object, this traveler from somewhere else, will make its closest approach to the sun, while we can't see it, while it's performing the cosmic equivalent of a high-speed turn behind a curtain. If something changes, if something moves in a way it shouldn't, we'll know. The numbers don't lie, the trajectory will tell the story. But if it doesn't, well, that might be even more interesting, because in the months leading up to this moment, something else disappeared. Something that should never go dark during a once-in-a-generation cosmic event. NASA's public information pages, gone quiet, right when we needed them most. And into that silence stepped the only people still watching, amateurs, backyard astronomers, citizen scientists with telescopes you could fit in a garage. What they captured sparked a wildfire of questions. A jet of material pointing toward the sun, not away from it. Features that didn't make sense, images that professionals couldn't immediately explain. Was it natural? Was it something else? The clock is ticking, and we're about to find out what happens when an interstellar visitor performs its most critical maneuver, in complete darkness. This is the story of 3I Atlas, and the amateur images that exposed a secret NASA didn't want you to know. Let's rewind. Let's go back to where this story really begins. July 1st, 2025. A telescope in Chile, part of the Atlas network, the Asteroid Terrestrial Impact Last Alert System, sweeps across a patch of sky it's scanned 1,000 times before. But tonight, there's something new, a faint smudge, moving. Not like an asteroid. No, this thing is racing through space with a velocity that makes astronomers sit up straight in their chairs. The preliminary numbers come in, and the team runs them again because surely they've made a mistake. They haven't. This object is moving on a hyperbolic orbit, eccentricity greater than 1. Way greater than 1, actually, around 6.1. Now, if you're not an orbital mechanics nerd, let me translate. Anything with an eccentricity above 1 is not gravitationally bound to the sun. It came from somewhere else, and it's leaving. This isn't an asteroid that got kicked out of the Kuiper Belt. This isn't a comet nudged by Jupiter. This came from out there. The designation happens fast. See 2025 N1, parentheses Atlas. But that's just paperwork. What matters is the other name, 3I Atlas. The I stands for Interstellar, the third interstellar object we've ever confirmed. After Oumuamua in 2017, that weird cigar-shaped tumbler that confused everyone, and Tai Borisov in 2019, the red comet that looked almost too normal. Now we have this. The orbit gets refined over the next few days, and here's what we learn. 3I Atlas is coming in on a retrograde trajectory, meaning it's traveling in the opposite direction most objects in our solar system move, an inclination of about 175 degrees, nearly polar. Its inbound velocity, its speed from infinity, as the astronomers call it, 58 kilometers per second relative to the sun. When it reaches perihelion, its closest point to the sun on October 29th, it'll be absolutely screaming at 68 kilometers per second. Perihelion distance, 1.36 astronomical units. That's about 204 million kilometers from the sun, closer than Mars. But here's the kicker. On December 19th, it'll make its closest pass to Earth at about 1.8 AU, roughly 270 million kilometers. Don't worry, we're safe. The minimum orbit intersection distance, the MOID, is about 0.36 AU. No impact risk. This visitor is just passing through. Mars gets a closer look in early October. The orbiter's there, circling the red planet. Snap images as 3I Atlas rushes past. We'll come back to those. But here's what matters right now, in July, as the discovery ripples through the astronomical community. We have months to study this thing. Unlike Oumuamua, which we caught on its way out of the solar system and had only weeks to observe, unlike Borisov, which was dimmer and less active, 3I Atlas is bright, it's active, and we have time, or so everyone thought. August, September, early October. The big guns swing into action. Hubble, the grand old eye in the sky, captures the first detailed images, a clear coma, that fuzzy cloud of gas and dust around the nucleus, and a tail streaming behind it. Classic comet behavior. JWST, the James Webb Space Telescope, the most powerful infrared observatory humanity's ever built, turns its instruments toward 3I Atlas and finds something weird. The carbon dioxide to water vapor ratio is off, way off. Some analyses suggest it's about 8-to-1, 8 parts CO2 to 1 part water. That's unusual. Most comets we've studied from our solar system are dominated by water ice. CO2 is there, sure, but not at these levels. What does it mean? Well, it could mean 3I Atlas formed in a colder, more carbon dioxide-rich region of its home star system, a place where water froze after the CO2, locking it deeper in the nucleus. Or it could mean something about the environment where it was born, billions of years ago, in a stellar nursery we'll never see. Gemini South, the massive telescope in Chile, tracks 3I Atlas night after night. The images show growing activity. The coma is expanding. Dust production is ramping up. This thing is waking up as it gets closer to the sun. And then, the 2-meter twin telescope in Spain captures something that makes the internet explode. A composite image, crystal clear. And there, undeniable, is a jet of material pointing toward the sun, not away from it, not trailing behind like a normal tail, toward the sun. The Astronomer's Telegram publishes it. Live Science picks it up. The article spreads like wildfire. Now, here's where it gets complicated. In comet science, jets aren't unusual. Rotating nuclei with active regions can blast material in all directions. You get fan-shaped jets, side jets, even jets that appear to point sunward because of viewing geometry and something called an anti-tail. But this image, it's stark, it's clear. And to anyone not steeped in the nuances of cometary physics, it looks wrong. The Unistellar network, a global community of amateur astronomers with smart telescopes, starts logging observations. 50, 60, 70 observations in the early months. And here's the thing that blows everyone's mind. 3I Atlas, at around magnitude 17.8 during some observations, becomes the faintest object the Unistellar network has ever successfully captured. Think about that. Thousands of citizen scientists pointing telescopes from their backyards, driveways, and rooftops, catching photons that traveled for who knows how long through the galaxy, just to land in their detectors. But some of those amateur images show things that are hard to explain. One video, posted by an observer using the handle Dobsonian Power, goes semi-viral. The narrator's voice is tinged with confusion and excitement. There's a cone, there's something in the middle. Alm's processed images show elongated features, strange asymmetries, structures that could be dust and gas behaving exactly as expected, or could be something else. The SETI Institute, yes, that SETI, the search for extraterrestrial intelligence, features 3I Atlas in their citizen science campaigns. Not because they think it's aliens, but because this is a perfect opportunity to refine orbital data, monitor dust activity, and train the global community on precision observations. Amateurs are helping professionals tighten the trajectory models. Every observation, every data point, makes the picture sharper. By mid-October, the momentum is huge. Papers are being drafted. Spectroscopic data is pouring in. Teams are planning observations through perihelion and beyond. And then, something else goes dark. October. The countdown to perihelion tightens. And if you go to NASA's website, NASA Science, the public-facing portal where they share updates on asteroids, comets, and space missions, you see a banner. Due to a lapse in federal government funding, NASA is not updating this website. A shutdown, not a cover-up, not a conspiracy, just bureaucratic dysfunction at the worst possible time. Because right now, as 3I Atlas barrels toward its closest approach to the Sun, as it enters the most scientifically critical phase of its journey, the public information pipeline, frozen. No updates on NASA's small body database. No fresh explainers, no press releases. The professionals are still working, of course. Scientists at JPL, at Goddard, at universities around the world. They don't stop because of a funding lapse. But the public is left in the dark. And you know what happens when you leave a vacuum? Something rushes in to fill it. Social media explodes. Reddit threads multiply. YouTube videos with titles like NASA Silent as Interstellar Comet Approaches rack up hundreds of thousands of views. Some of it's harmless speculation. Some of it's less harmless. Claims of secret observations, allegations of data suppression, theories that spiral into territories where evidence gets creative. And look, let's be clear. NASA's Tom Statler, program scientist for the Planetary Defense Coordination Office, goes on record multiple times. It looks like a comet. It's behaving like a comet. All the data we have is consistent with a natural object. Other scientists echo this. The mainstream consensus is solid. 3I Atlas is fascinating, yes. Interstellar, absolutely. But alien technology? The data doesn't support it. But when the official channels are silent, when the authoritative voices aren't amplified through the usual channels, the fringe gets louder. And the questions start to sound less ridiculous. Why now? Why does this shutdown happen during the exact window when we need public engagement most? Why is the most significant interstellar visitor we've ever had a chance to study comprehensively disappearing behind the sun during a moment when NASA can't even update a web page? The answer, of course, is mundane. It's politics, it's timing, it's bad luck. But the perception is that something's being hidden. And so, the citizens step up. Because here's the beautiful, incredible thing about modern astronomy. You don't need NASA's website to do science. You need a telescope, a camera, software, and the will to point it at the sky. The Unistellar network doesn't stop. They can't stop. Every clear night, telescopes across the globe, synchronized through an app, slew to 3I Atlas and capture frames. 50 observations become 70, then 90, then over 100. Magnitude 17.8. Faint. Ridiculously faint for a distributed network of small telescopes. But they get it. And it's not just pretty pictures. These observations are science. Astrometry, the precise measurement of an object's position against background stars, is how we refine orbits. Every observation narrows the uncertainty. Every data point submitted to the Minor Planet Center makes the trajectory models tighter. The amateurs are doing real work. Then, on October 21st, 3I Atlas enters solar conjunction. From Earth's perspective, it passes behind the Sun, or rather, close enough in angular separation that observing it becomes impossible. The glare, the risk of pointing instruments near the Sun, it's too much. For Earth-based observers, the lights go out. But the amateurs have already done something crucial. They've filled the gap. While NASA's public pages were frozen, while the official updates stalled, citizen scientists built a continuous observational record. They captured the pre-conjunction images, they documented the jet, they logged the brightening, the coma growth, the dust activity. And they proved something that NASA, ESA, every space agency should tattoo on their walls. You cannot do 21st century space science without the public. The era of ivory tower astronomy, where discoveries are announced from on high, and the masses just wait over. But there's something else. Something the amateurs revealed that goes beyond pretty images and orbital data. Because as 3I Atlas vanished behind the Sun, as the countdown to perihelion hit 0, a plan was unfolding. A plan that had been in motion for months. A plan that would turn 3i Atlas into something more than just a scientific curiosity. It would become a test. Okay, let's get something straight. What makes an object interstellar? Because that word gets thrown around a lot. And if we're going to talk about 3i Atlas, if we're going to evaluate the claims and counterclaims, we need to understand the rules. In orbital mechanics, there's a number that matters above almost everything else. Eccentricity. Eccentricity tells you the shape of an orbit. 0, that's a perfect circle. Between 0 and 1, that's an ellipse, like Earth around the Sun, or a comet in a long stretched loop. But when eccentricity equals 1, you get a parabola. An open curve, the object is on the edge of escape. And when eccentricity is greater than 1, that's a hyperbola. That object is not bound to the sun. It's passing through. It came from somewhere, and it's leaving for somewhere else. 3-eyed, Atlas has an eccentricity of about 6.1. 6.1. That's not borderline. That's not, maybe it got kicked out by Jupiter. That's decisively interstellar. And then there's the inbound velocity from infinity. V infinity. That's the speed the object would have if it were infinitely far from the sun, unaffected by solar gravity. For 3i Atlas, 58 kilometers per second. To put that in perspective, Voyager 1, the fastest human-made object to leave the solar system, is crawling at about 17 kilometers per second relative to the sun. 3i's Atlas is moving more than 3 times faster. And it's coming at us retrograde. It's moving in the opposite direction that the planets orbit. Picture this. The solar system is a highway where all the cars are moving clockwise. 3i Atlas, it's barreling down the other side of the road at 200,000 kilometers per hour. So, yes, interstellar is confirmed. No debate, no question. But here's where it gets interesting. Oumuamua, the first interstellar visitor we confirmed back in 2017. It was weird. Cigar-shaped, or maybe pancake-shaped, depending on who you ask. Tumbling. No visible coma or tail. And it showed evidence of non-gravitational acceleration. A tiny but measurable push that couldn't be explained by just the sun's gravity. That kicked off years of debate. Natural outgassing, a light sail, a chunk of solid hydrogen. The papers are still being written. Then came 2i Borisov in 2019. And Borisov was almost boring. It looked like a comet. It acted like a comet. Reddish color, normal composition. The science was fascinating, don't get me wrong, but there were no mysteries. So, where does 3i Atlas fit? Well, it looks like a comet. Jets, coma, dust, tail, the whole package. But the details are where things get interesting. So let's talk about that jet, that sunward jet, the image that broke the internet, the feature that made even professional astronomers do a double take. Because here's what should happen with a comet. As it approaches the sun, solar radiation heats the nucleus. Ice sublimates, turns directly from solid to gas. That gas, carrying dust particles, streams away from the sun, pushed by solar wind and radiation pressure. Away, not toward. That's why comet tails always point away from the sun. Even when the comet is leaving the inner solar system, the tail doesn't trail behind like the exhaust from a rocket. It's pushed. So, when amateur astronomers and then professional observatories start capturing images of 3i Atlas with a clear, visible structure pointing toward the sun, yeah, people notice. Now, here's where comet physics gets fascinating. Comets don't just have one tail. They can have 2, sometimes more. There's the dust tail, yellowish-white, curved, broad. That's sunlight reflecting off dust particles. Then there's the ion tail, bluish, straight, narrow. That's ionized gas molecules being carried by the solar wind at incredible speeds. But there's another phenomenon, something that's rarer but totally natural. The anti-tail. See? Here's what happens. Imagine you're looking at a comet from Earth. The comet has a broad, flat disk of dust particles spread along its orbital plane. As the comet moves and our perspective changes, sometimes we look through that dust disk's edge on, and when that happens, the dust particles between us and the comet appear to point toward the sun. It's not actually moving sunward, it's a viewing geometry illusion, like seeing a frisbee edge on versus face on. So, problem solved, right? The sunward jet is just an anti-tail. Next question. Except, not everyone agrees. The 2-meter twin telescope in Spain publishes their composite. Live Science runs an article. The image supports the presence of a fan-shaped sunward jet, consistent with active outgassing from a rotating nucleus. See, comet nuclei aren't smooth, uniform ice balls. They're lumpy, irregular, with active regions, hot spots where volatiles are concentrated. As the nucleus rotates, these active regions swing into sunlight, then back into shadow. The jets turn on and off, and depending on the angle, the spin rate, and the location of those active regions, you can get jets pointing in directions that seem wrong, but are perfectly natural. But here's where it gets spicy. Avi Loeb, the Harvard astrophysicist who's become, let's say, famous for his willingness to consider exotic explanations, he points out that the sunward features could be evidence of something more than outgassing, directed thrust, intentional maneuvering, a probe performing course corrections. Most comet scientists disagree strongly. They point to cases like Comet Hale-Bopp, which showed complex fan-shaped jets, or Comet 67P Churyumov-Gerasimenko, which the Rosetta spacecraft studied up close, revealing jets erupting from cliffs and pits in wildly different directions. Comets are weird. Their behavior can look anomalous until you understand the physics. But here's the thing that keeps this debate alive. We've never observed an interstellar comet with this level of detail during approach. Borisov was dimmer, less active. Oumuamua had no visible coma at all. 3I Atlas is unique. And the jets? They're just the beginning of the strangeness. Let's talk about what this thing is made of. Because chemistry is destiny. The composition of a comet tells you where it formed, when it formed, and under what conditions. It's a fingerprint, a biography frozen in ice. So when JWST, the James Webb Space Telescope, turns its infrared eyes toward 3I Atlas and starts analyzing the coma, the scientists are expecting to see a lot of water vapor, because most comets are water-rich. H2O is the dominant volatile. But that's not what they find. The carbon dioxide to water ratio is about 8:1, 8 parts CO2, 1 part water. Now, if you're not a cometary chemist, you might think, so what? It's just a different mix of gases. But here's why this matters. In a protoplanetary disk, the swirling cloud of gas and dust around a young star where planets and comets form, temperature is everything. Close to the star, it's hot. Rocky planets form, metals condense. Farther out, past the snowline, it's cold enough for water ice to condense. Even farther out, in the coldest regions, carbon dioxide, carbon monoxide, methane, these supervolatiles can freeze solid. So, a comet rich in CO2 and relatively poor in water. That suggests it formed farther out, in a colder region of its home star system, than typical solar system comets. Or it formed a long time ago, in an environment where the chemical mix was just different. But wait, there's more. The Very Large Telescope in Chile, VLT, conducts spectroscopic observations. They detect cyanogen, CN, that distinctive molecule that gives comets their greenish glow, and nickel vapor. Nickel. Now, nickel in cometary comae isn't unheard of. Papers published in recent years have detected nickel and iron in solar system comets, likely from metal-bearing dust grains being vaporized by the sun's heat. So, finding nickel in 3I Atlas? Not necessarily strange, but the levels, the ratios, those are still being debated in preprints and conference papers. Spectroscopy Online publishes a technical recap. Rotation period estimated at about 16.16 hours. Dust mass loss between 0.3 and 4.2 kilograms per second, depending on the observation window. And here's a key detail. The dust grains are large. When dust grains are large, they're less affected by radiation pressure. They don't get pushed away as easily. Result? An asymmetric coma, a low, stubby tail, the kind of structure that can look odd in images, especially to untrained eyes. I spoke with a cometary chemist who explained it like this. Interstellar comets can have different compositions. They formed in different stellar environments, possibly billions of years ago. Different temperatures, different chemical abundances, different formation timescales. But different doesn't mean artificial. It means we're looking at a sample of processes happening across the galaxy. And that's the incredible thing, right? 3I Atlas isn't just a comet, it's a messenger, a bottle tossed into the galactic ocean, drifting for possibly 7 to 10 billion years, carrying a message about a star system we'll never see, a place and time so remote we can barely imagine it. But here's the question that won't go away. If this chemistry is natural, if the jets are natural, if everything we're seeing has a conventional explanation, why are some very smart people still suggesting it might not be? Okay, let's address the elephant in the observatory, the A word, alien. Specifically, let's talk about Avi Loeb's list. Professor Abraham Loeb, chair of Harvard's Astronomy department, founder of the Galileo Project, author of multiple books on the search for extraterrestrial intelligence. He's published a series of analyses on Medium and in academic preprints outlining what he calls anomalies associated with 3IZ Atlas. Now, before we dive in, let's be clear. Loeb is a respected scientist. His credentials are impeccable, and science needs people willing to ask uncomfortable questions. But his interpretations are not consensus. Here are the key points he raises. 1. The orbital alignment. 3I. Atlas's trajectory brings it into the inner solar system at a time when Earth-based observation is maximized before solar conjunction. Loeb suggests this could be intentional. 2. The sunward jet. He argues that the directionality and persistence could indicate propulsion rather than outgassing. 3. The timing. The object's perihelion coincides with solar conjunction, providing a blind spot for detailed observation at the most critical moment. 4. The speed and trajectory. The retrograde orbit and high velocity could, in his view, be consistent with a deliberately chosen path. 5. Polarization claims. Preliminary analyses suggest unusual polarization in the coma that might not fit standard dust models. 6. The wow signal alignment. This is speculative. Loeb notes that 3I Atlas's trajectory, if extended backward, passes relatively near the direction of the famous 1977 wow radio signal. This is a stretch by most accounts. 7. The mass and activity levels. The balance between inferred nucleus size and observed outgassing could, he suggests, be tweaked for observability. 8. The overall probability. Loeb has publicly stated that he assigns a non-zero probability, sometimes as high as 10 to 20% in informal discussions, that 3I Atlas could be artificial or related to technology. Now, let's talk about the response. NASA's Tom Statler, multiple times on record. This object looks like a comet. It behaves like a comet. Every measurement we have is consistent with natural processes. Other comet scientists, planetary defense experts, dynamicists, they push back hard. The orbital alignment, selection bias. We discover objects that are bright and observable. Of course we find them when they're in favorable geometry. The sunward jet, anti-tail plus fan-shaped active regions, seen before on other comets. The timing of solar conjunction, pure coincidence. Perihelion date is determined by orbital mechanics, not intent. The polarization, preliminary data. Large dust grains can produce unusual polarization. More observations needed. The wow signal alignment. The wow signal came from a direction in Sagittarius. The sky is big. Trajectories pass near lots of things. And as for the 10 to 20% probability of artificial origin, most scientists would put that number at less than 1%, maybe much less. But here's the thing, and this is where the story gets interesting. Loeb is right about one thing. The way to settle this? The way to move from speculation to knowledge. Test it. Make a prediction. Set a falsifiable threshold. And 3i Atlas is about to give us that chance. Because if this object were artificial, if it were a probe, a spacecraft, anything with propulsion, there's one moment where it would be stupid not to use it. Perihelion. It's called the Oberth effect. When you're deep in a gravity well, moving at high speed, any thrust you apply gets amplified. If you fire a rocket engine at perihelion, the change in your trajectory is much bigger than if you fire that same engine out in interstellar space. So if 3i Atlas were going to maneuver, to change course, to drop probes, to do anything that requires energy, perihelion is the place to do it. And perihelion happens on October 29th, 2025, behind the sun, where we can't see it. Okay, so, problem. We have this perfect natural experiment, the most important moment in 3i Atlas's pass through the inner solar system, and we're blind. From Earth, 3i Atlas enters solar conjunction on October 21st. Solar conjunction means the object is close enough to the sun in the sky that observing it is either impossible due to glare or dangerous because you risk pointing telescopes too close to the solar disk. Perihelion happens 8 days later, on the 29th. So, during the exact window when we'd want continuous high-precision tracking, Earth-based observatories go dark. But we're not completely blind, because we have eyes in other places. GOES-19, the geostationary operational environmental satellite, is mentioned in some analyses. Its coronagraph instruments, designed to monitor the sun's corona, might catch 3i Atlas if the geometry is favorable. It's a long shot. GOES isn't designed for comet tracking, but maybe. ESA's JWST spacecraft, JWST, the Jupiter Icy Moons Explorer, is currently on its way to Jupiter. In early November, its trajectory brings it to a position where, potentially, its instruments could observe 3i Atlas from a different angle. But here's the catch. JWST is far away. Its instruments aren't optimized for faint comets. And whether anyone actually tasked JWST to observe 3i Atlas, that information is not public yet. Mars. Remember, 3i Atlas made a relatively close pass to Mars in early October. The orbiters there, MAVEN, Mars Odyssey, the European Mars Express, possibly even the cameras on Perseverance and Curiosity, they captured images. Those images are gold. Different vantage point, different lighting geometry, potentially catching features Earth-based observers missed. But as of right now, most of those images haven't been publicly released. And then there's Jupiter. On March 16, 2026, 3i Atlas will pass within about 54 to 60 million kilometers of Jupiter. Juno, NASA's Jupiter orbiter, is there. Its suite of instruments, ultraviolet, infrared, radio. Could they observe 3i Atlas? Technically, maybe, if the geometry works. If someone submits a proposal and it gets approved. If Juno's instruments can be retasked. But that's a lot of ifs. So, as October 21st arrives, as 3i Atlas slips behind the sun, the global astronomical community holds its breath. Because here's the brutal truth. If something extraordinary happens at perihelion, if there is a maneuver, a trajectory change, an anomaly, we might not know for days. Not until 3i Atlas reemerges in mid-November, far enough from the sun for Earth-based telescopes to reacquire it. And by then, any evidence would be indirect, retroactive. We'd be looking at a trajectory that changed, trying to figure out when and how. But here's what the amateur images revealed. Here's the secret that NASA didn't want out in the open. Not because it's sinister, but because it's embarrassing. So, what was the secret? The secret is this. Our infrastructure for monitoring and communicating about once-in-a-generation cosmic events is fragile. When a government shutdown freezes NASA's public-facing websites, when the usual channels for updates, explainers, and data visualization go silent, a vacuum forms. And into that vacuum rushes speculation, misinformation, and fear. But the amateurs didn't just fill the vacuum with noise, they filled it with data. While NASA's webpage displayed that shutdown banner, while official press releases slowed to a trickle, citizen scientists were working. Unistellar network observers, backyard astronomers with Dobsonians, university clubs with modest telescopes. They kept the observational record continuous. They submitted astrometry to the Minor Planet Center. They processed images and shared them on forums, Twitter, Reddit, Discord servers. They became the bridge. But here's what most people don't know. Behind the scenes, there was a plan. The International Asteroid Warning Network, IAWN. IAWN is a UN-endorsed global collaboration of space agencies, observatories, and research institutions. Its job? Coordinate observations of near-Earth objects, refine threat assessments, and train the planetary defense community. And in late October, IAWN makes an announcement. IAWN selects 3I Atlas for a global observing campaign, November 27, 2025 through January 27, 2026. Objective: train observers in precise cometary astrometry. Translation: 3I. Atlas isn't just a scientific curiosity. It's a stress test. Think about it. An interstellar visitor, moving fast, brightening, approaching Earth for a close pass in December. It's the perfect target to practice on. Because here's the nightmare scenario that keeps planetary defense coordinators awake at night. What if we discover an asteroid or comet on a collision course with Earth? And our observing network isn't ready? What if we can't get accurate astrometry fast enough? What if our coordination systems fail? 3I Atlas is the drill. And the amateur community? They're not just spectators, they're participants. IAWN's campaign explicitly invites smaller observatories, university programs, and citizen science networks to contribute. Because the next potentially hazardous asteroid we need to track, it might not be bright, it might not be easy. We need thousands of eyes, distributed globally, capable of precise measurements. And we need to train them now on a safe target. So when it matters, we're ready. So, the secret the amateur images exposed? It's not a cover-up of alien technology. It's not NASA hiding data. The secret is that our official systems, the websites and press releases and public communications, they're vulnerable. They can go dark at exactly the wrong moment. But the network, the global community of professionals and amateurs, institutions and individuals, that is resilient. That kept working. And when you look at the full picture, the arc of this story, 3I Atlas becomes something more than a comet. It becomes a mirror showing us our strengths, our weaknesses, our readiness for the next chapter of planetary defense and interstellar science. And now, the clock hits 0. October 29th, 2025. Perihelion, 68 kilometers per second, 136 million miles from the sun, hidden from Earth, and somewhere out there, behind the blinding glare of our star, 3I Atlas makes its turn. October 29th, 1.36 astronomical units from the sun, 68 kilometers per second. That's 152,000 miles per hour, fast enough to cross the United States in 30 seconds. And somewhere in that inferno of solar radiation, plasma, and magnetic fields, 3I Atlas makes its closest approach. Now, here's what we need to understand about this moment. If 3I Atlas were artificial, if it had any capability for propulsion, any engines, any maneuvering thrusters, this is when you'd use them. It's called the Oberth effect, named after Hermann Oberth, one of the founding fathers of rocketry. Here's the concept. When you're moving at high speed, deep in a gravity well, the kinetic energy you ADD through thrust gets multiplied. Think of it like this. If you're standing still and you push a shopping cart, it moves at a certain speed, right? But if you're already running and you push that same cart with the same force, it goes much faster. The same principle applies in space. Fire your engine when you're screaming past the sun at 68 kilometers per second. That delta V, that change in velocity, gets amplified by your existing momentum. You get more trajectory change for the same amount of fuel. So if 3I Atlas were going to do something, drop a probe, change course, reveal its true nature, perihelion is the only moment that makes sense. But how would we know? Great question. Because remember, we can't see it during perihelion. Earth-based telescopes are blind. So the evidence would be indirect. Here's what astronomers would look for when 3I Atlas reemerges in mid-November. 1. Astrometric residuals. That's the difference between where the object should be, based on gravitational calculations, and where it actually is. If 3I Atlas received a push at perihelion, even a small one, its position would be off. Not by much. Maybe a few arcseconds, but measurable. 2. Non-gravitational accelerations. Comets naturally show these because of outgassing. The jet forces act like tiny rocket engines. But if the acceleration is larger than expected, or in the wrong direction, or shows a pattern that doesn't match outgassing models, red flag. 3. Sudden changes in photometry. If 3I Atlas suddenly gets brighter or dimmer in a way that doesn't match the expected sun-distance relationship, if the coma structure changes dramatically, if new features appear that weren't there before, that would demand an explanation. 4. Object multiplicity. If 3I Atlas dropped probes at perihelion, we might start seeing multiple objects where there was one, tiny faint dots separating from the main nucleus. That would be unambiguous. So those are the tests, those are the criteria. And as November arrives, as the conjunction window closes and Earth-based telescopes start reacquiring 3I Atlas, the data starts flowing in, and the answer is, it's a comet, the astrometry, matches gravitational predictions within error bars. The photometry, consistent with natural outgassing and sun distance effects. The non-gravitational accelerations, present yes, but exactly what you'd expect from asymmetric jet activity on a rotating nucleus. No sudden course changes, no probe releases, no multiplicity. 3I Atlas behaves like a comet. And you know what? That's not a letdown. That's extraordinary. Because here's what we just witnessed. The most comprehensively observed interstellar comet in human history. Oumuamua, we caught it on the way out. We had weeks, and most of that was spent just confirming it was interstellar. Borisov, dimmer, less active. Important, yes, but harder to study. 3I Atlas, we tracked it for months, from discovery in July, through approach, through peak activity, through perihelion, and now through departure. Hubble, JWST, Gemini, VLT, SALT, NOT, Mars orbiters, and hundreds of amateur astronomers. We have spectroscopy, photometry, polarimetry, astrometry, morphological studies, rotation curves, dust production rates, gas composition. We have a data set. And what does that data tell us? 3I Atlas is a time capsule, a messenger from the early days of our galaxy. Preliminary orbital reconstructions suggest it came from the galactic thick disk. The thick disk is old, 7, 8, maybe 10 billion years old. Our sun, 4.6 billion years old. 3I Atlas was wandering through space before our solar system existed. Think about that. This chunk of ice and rock and organic molecules, it formed around a star that might not even exist anymore. It drifted through the galaxy for billions of years, past supernovae, through molecular clouds, across spiral arms. It saw the galaxy evolve, and its chemistry tells a story. That CO2-rich water-poor composition? It suggests formation in a colder region than most solar system comets. The nickel vapor, the cyanogen, the dust characteristics. They're slightly different from what we see in our local comets. Not alien, not artificial, just foreign. A different stellar environment, a different formation history. And the jets, the anti-tail, the sunward features that sparked so much debate, natural, explainable, consistent with active comets we've studied up close, but also a lesson. A lesson that even natural phenomena can look anomalous when we don't have the full picture. A lesson that extraordinary claims require extraordinary evidence, yes, but ordinary claims require thorough investigation too. And here's the real payoff. The reason this matters beyond the science. 3I Atlas was a rehearsal, a dress rehearsal for the era we're about to enter. The Vera C. Rubin Observatory, the Legacy Survey of Space and Time, LSST, it comes online next year. And when it does, it's going to discover dozens, maybe hundreds of interstellar objects per year. Right now, we found 3, total, ever. In a few years, we'll be swimming in data. And 3I Atlas taught us how to be ready. It tested our networks, our communication systems, our ability to mobilize global resources quickly. It tested our amateur community, and they passed with flying colors. It stress-tested the IAWN framework for planetary defense coordination. And it reminded us of something we sometimes forget in the age of billion-dollar space telescopes and AI-driven data analysis. Science is not just for professionals. Science is not just for people with PhDs and access to Hubble. Science belongs to anyone with curiosity, patience, and a willingness to point an instrument at the sky. And that is why 3I Atlas matters. Okay, so the story's over, right? 3I Atlas behaves naturally. We learned a ton. Case closed. Wrong, because 3I Atlas isn't leaving yet. And there are dates, specific dates, that you're going to want to circle on your calendar. Date number 1, mid-November, 2025. This is when 3I Atlas fully re-emerges from behind the sun. Earth-based observatories get their first good looks at post-perihelion activity. What are we watching for? Changes in jet morphology. Did the jets get stronger, weaker, or change direction? Coma structure. Is it expanding, contracting, fragmenting? Dust production. Did perihelion heat trigger new outgassing regions? And, of course, any astrometric residuals that might suggest something we didn't expect. Date number 2, December 19th, 2025. This is the big one for amateur astronomers. Closest approach to Earth, about 1.8 AU, roughly 270 million kilometers. That's still distant, but it's as close as 3I Atlas gets to us. For Northern Hemisphere observers, visibility will be excellent in December and January. Magnitude estimates suggest it could be as bright as magnitude 9 or 10 at closest approach. That's visible in good binoculars under dark skies. Easily captured by amateur telescopes. And this is where the IAWN campaign really kicks into high gear. From November 27th through January 27th, the International Asteroid Warning Network is inviting observers worldwide to participate, submit astrometry, capture images, practice precise measurements. This is citizen science in action. And the data you collect, it's not just for fun. It goes to the Minor Planet Center. It refines the orbit. It trains the algorithms. It builds the infrastructure for real planetary defense. Date number 3, March 16th, 2026. This is the wild card. 3I Atlas passes within about 54 to 60 million kilometers of Jupiter. Now, that's not a close pass by any means, but NASA's Juno spacecraft is orbiting Jupiter, and Juno has instruments that could, potentially, observe 3I Atlas from a completely different vantage point. UV spectrographs, infrared sensors, radio wavelength detectors. Whether Juno actually observes 3I Atlas depends on a lot of factors. Instrument availability, pointing constraints, mission priorities. But if they do, we get a 3-dimensional view of the coma. Composition data from angles Earth can't access. Potentially, measurements of the solar wind interaction at Jupiter's distance. That's scientifically juicy. So, here's what you can do. If you have access to a telescope, even a small one, check out the IAWN campaign details. Links are in the description. If you're part of a local astronomy club, organize an observing session. If you have a Unistellar telescope or similar, Submit your observations. If you don't have a telescope, follow the professional observations. Papers will be published over the next year. NASA's small body database will update. The shutdown will eventually end, and we'll get comprehensive data releases. Join online communities, ask questions, learn the science. Because this is how astronomy works now. It's not locked behind university walls. It's not exclusive to people with million-dollar grants. It's collaborative. It's global. It's open, and if something does turn up, some unexpected anomaly, some data point that doesn't fit, you'll be part of the community that finds it. So, let's come back to where we started. What did the amateur images really reveal? They revealed continuity. When official channels went dark, when NASA's website froze, when the infrastructure we thought was solid cracked, the amateur community stepped in. They kept the observational record intact. They posted their data. They shared their images. They asked questions. They refused to let the story go silent. And the secret they exposed? It wasn't alien technology. It wasn't a government cover-up. The secret was this: our systems for public engagement with science, for communicating discoveries in real time, for democratizing access to cosmic events. They're more fragile than we want to admit. A government shutdown silences NASA's public pages. A solar conjunction blinds our Earth-based telescopes. And in those gaps, those moments of vulnerability, we rely on the network, not the technological network, though that's part of it. The human network, the amateur in Spain capturing frames until 3 a.m., the PhD student in Chile processing spectroscopy data, the retired engineer in Texas submitting astrometry, the high school club in Japan organizing an observing night. That network is unbreakable. But there are questions that remain. Why is 3I Atlas so CO2 rich? What does that tell us about the conditions in the galactic thick disk 7, 8, 10 billion years ago? Will we detect subtle non-gravitational accelerations in the long-term astrometry? Nothing dramatic, nothing that screams artificial, but something that teaches us about outgassing physics we don't fully understand yet? How many more interstellar visitors are out there? When Rubin comes online, when we start discovering dozens per year, what will we learn about the diversity of planetary systems across the galaxy? And the big one, when we do encounter something that's genuinely unambiguously anomalous, something that breaks the models, that defies natural explanation, that forces us to consider other possibilities, will we be ready? Will our networks be strong enough? Will our infrastructure hold? Will we have the humility to listen to all voices, amateur and professional, skeptical and open-minded? 3I, Atlas gave us a blueprint, a test case, a rehearsal, a lesson. It reminded us that the universe doesn't wait for our budgets. It doesn't pause for political dysfunction. It doesn't care about our readiness. Cosmic events happen on their schedule, and it's up to us to be ready. The next interstellar visitor, it might arrive next year. It might be decades from now, but when it does, when that next traveler from beyond our solar system enters our neighborhood, we won't be caught unprepared. We'll have our telescopes ready, our networks primed, our community watching, and somewhere, in a backyard observatory, on a rooftop in a city, through a telescope pointed at a patch of sky that looks empty, someone will catch the first photons. Someone will see it first, and the story will begin again. This has been the story of 3I Atlas, the interstellar visitor that exposed not a conspiracy, but a truth. That science belongs to all of us. And the universe? The universe is ours to explore. Keep watching the skies.